We now come to atomic models where people started explaining what the atom looked like. We're going to start with a little history. Back in 400 BC, Greek philosophers felt that the atom was an indivisible object whose shape depended on its macrophysical properties. For example, water atoms would be slippery, and iron atoms would be very solid and hard. It wasn't until 1802, so what's that, 2200 years later, when John Dalton, based on experimental research, again, experimental research, proposed that elements were made up of specific atoms, and these atoms would combine with each other. They were indivisible. Again, so we still have the indivisible part, and could not be altered by any chemical means. So this worked on disproving the alchemists who thought they could add chemicals to various elements and change them into different elements. Then the models evolved very rapidly, starting with Thomson's discovery of the electron. Thomson's discovery of the electron was the first evidence that the atom had an underlying structure. So in 1904, he proposed that the electrons that he discovered, and here they are, see the electrons, the little negative charges here, are moving about within a mass of positive charge. You can see this positive sign here. He never really said what the positive charges were. It was just kind of this amorphous mass. And it was nicknamed the Plum pudding model. Now, for people here in the US, that doesn't make a whole lot of sense until you realize that it's an English dessert where raisins, okay, which used to be called plums in England, are embedded in an egg, suet, and molasses mixture, hence the nickname, plum pudding. However, and this is going to be a continuing thread, as new models were proposed and analyzed, they found out that they could explain some phenomena of the atom, but not all. And in this case, the plum pudding model could not explain the different wavelengths of light emitted by excited atoms. The plum pudding model only lasted 5 years. And what was pretty interesting about it is that the work done by one of Thomson's own students, Ernest Rutherford, and then Hans Geiger and Ernest Marsden, established that the positive charge of this model was concentrated in a tiny nucleus of diameter 10 to the minus 15th meters. So instead of this whole amorphous blob here, you would have the positive charge concentrated right there in the middle. The way they found this out is they aimed a beam of alpha particles at a piece of gold foil. If the atom were a plum pudding and this positive charge here was dispersed throughout it, they would expect that these heavy alpha particles would just plow right through it and come back at the other side. Just like this model right here. You can see the alpha particles. This is what was expected. They would just go right through and be measured on the other side. However, instead of observing this, where the alpha particles would all come out here, what was observed was some were deflected. You can see this arrow here. We're going to look at the bottom picture here. This is what actually happened in the experiment. And a very few came right back at the alpha source like this. And to quote Rutherford, because this is one of those very famous statements, "It was quite the most incredible event that has happened in my life. It was almost as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you." A 15-inch shell is a naval weapon. It's very large. Frankly, it's about the size of a small car. So this is pretty amazing. Can you picture firing a car at tissue paper and having it come back and hit you? That's how much Rutherford was impressed by this experiment. Hence, it was concluded that the positive charge was all located right here in a tiny region of the atom, which would explain why most of the alpha particles got through, but every now and again, if you hit this nucleus, you'd have a particle either deflect or come right back at you. The other implication of this, with the positive charge being concentrated in a small nucleus, is that most of the atom is just empty space. However, for the small percentage of alpha particles that actually struck the nucleus, they would be deflected, and in the most extreme case, just bounce right back. Rutherford then proposed that the small nucleus was surrounded by electrons in planetary orbits. Why do you think Rutherford proposed planetary orbits to explain this? Scientists, and probably most people, when they're confronted with a new phenomena, like to draw upon previous history, previous knowledge to explain it. And scientists at the time were very well versed in planetary orbits, ever since Galileo, Copernicus, Bray, and Kepler. Also, notice the similarity in the force equations for gravity and the electric force. Here's the gravitational force, here's the electric force. Both have a 1 over r squared dependence. Both have a constant in front of them. And in gravity, the key operator are the masses. And in the electric force, it's the charges. So, since the equations are similar, and gravity causes planets to move in orbit about the sun, why wouldn't electrons do the same thing about the nucleus? Now, Rutherford did not propose a structure for these orbiting electrons. That would be left to Niels Bohr. To emphasize how much of the atom is just empty space, a void, if the nucleus was magnified so that it was size of a baseball, then the atom would have a radius of 4 kilometers, or 4 times 10 to the third meters. The electrons would be the size of the period at the end of this sentence. The below website presents a great simulation of Rutherford's gold foil experiment, so you can click on that and have a very nice simulation. Now, another thing Rutherford could not explain was the different wavelengths of light that were emitted by the excited atoms. That also would be left for Niels Bohr.